gluons in the atom's nucleus with beams of electrons from the superconducting accelerator. Jefferson Lab has an educational mission as well. The Jefferson Lab Science Series features scientists and engineers who are gifted in making their work not only informative but fun. The Science Series is held once a month in the Jefferson Lab Auditorium. The presentation is live, spontaneous, and unrehearsed.
Good evening. My name is Fred Dilla. I'm one of the physicists here at Jefferson Lab, and tonight we're going to test microphones. Just kidding. We're actually going to have a lecture that is much more interesting than microphones by a colleague and friend of mine from MIT, Dr. David Shoemaker. And tonight's lecture is about observing and detecting gravity waves, which you probably haven't thought about very much. You know about detecting light waves. We're all doing that right now. That's pretty easy to do. Radio waves, you know how to do that too. You have a radio at home. You need a little more sensitive instrumentation. But gravity waves are a much more difficult problem. You need a very sensitive detector. He's going to tell you about the antennas they're building in the state of Louisiana and the state of Washington. You need big flat states to put these antennas. They're about 16 kilometers long in total. And to measure gravity waves, you need something very sensitive, because when one goes by, it only wiggles the antenna about 1 billion times smaller than the size of an atom. We think we're doing tough things here when we look inside of an atom, but this guy's got a much tougher job. I have to tell you a little bit about Dr. Shoemaker. He's had a very interesting career leading to his present position at MIT on this gravity wave observatory project. He started out not as a physicist, but interested in playing guitars and rock bands. And his journey to a physicist began with a very good teacher at Tufts University who asked him to think about why does a guitar make music? And he wrote a thesis on the physics of guitars. And he could have continued on being a musician, I'm sure, but he decided to study physics and went on to another little school near Tufts University, MIT, and got his master's. They are working on another astrological problem, infrared satellite, very famous satellite that's still up there now, called the Kobe satellite. Well, he got a little tired of that and made a little trip across the ocean to Munich and started working at an institute outside of Munich on gravity wave detectors. And along the way, learned German and decided that really, if he's going to stay in this business, you really need a PhD. And he also decided it was time for cultural change, so he migrated west to Paris. And he finished his thesis at the University of Paris. And of course, you don't defend your thesis at the University of Paris in English or German, so he had to learn French. And that's a good place to do it. It's also where he met his wife, who I understand helped him learn French. And she is also a physicist, an astrophysicist. And they're both now living in Boston. He's back at MIT. And she's come full circle. She's gone back to a music career, and she's an opera singer. So this man has had a very interesting career, but that's what's possible when you study science and you study physics. You can kind of do what you want. So I will ask you to help me welcome Dr. Shoemaker, who's going to talk to you about gravity waves.
Thank you, Fred. So I'm going to tell you about the project that I'm working on. It's one that I have a lot of fun with. It's the LIGO project. It's a project to build observatories to look at gravitational waves. It's a little bit of a long talk, and so you know when to fall asleep. Here's the organization. There's the nature of gravity waves. I'm going to talk a little bit about how exactly we get our hands around the gravity waves. And I want to talk about some of the limitations to the sensitivity of our apparatus, because it lets you see some of the physics that's underneath the detection system, not so much the gravity waves themselves. And then lastly, I'll have some nice pictures to show what it looks like if you build this sort of installation out in the desert. Oh, just so we can get the acronym straight. What does LIGO stand for? It's the Laser Interferometer Gravitational Wave Observatory. As I say, it's a project to build these observatories. Each one is fairly large, 4 kilometers in length for each one of 2 arms, and then there are 2 sites. So it's got some big money associated with it, a lot of organizational stuff that goes along in addition to the science. We want to both enable an initial detection of gravitational waves, but then also go ahead and make an astronomy of gravitational waves possible, just the way optical telescopes or radio telescopes are used. It's a group effort of colleagues at MIT and Caltech. I'm at MIT. And there, just to give you a sense of how the group fits together, there are 5 graduate students, usually a couple of undergraduates who work with us as well on smaller projects, about 7 scientists, and then some engineers and some support staff. So it's a nice compact group, and we all sit together and drink coffee and argue. It's a nice environment. It is about 100 people in total, though, so it's not a tiny project. We're not alone. There are other efforts to build interferometric detectors. There's one in France and Italy, where curiously enough, the antenna is going to be built near Pisa, where the infamous experiment may or may not have happened, dropping things off. There's a German-Scots collaboration, there's a Japanese collaboration, and then there's a more far-flung project to build such a detector up in space. I won't have the time to talk about any of those other projects, but it's something that's happening around the world now. It's going to be a new important field in the year 2000 and beyond. What are gravitational waves? I'm going to make a lot of analogies to radio waves to try and give you something more familiar to hold on to as we go forward. But first off, let's talk about static gravity. We're familiar with that, of course. It makes apples fall, it makes the Earth orbit around the sun. And we have an expression that's pretty straightforward that shows you what the force is due to a pair of masses, supposedly maybe a big one and a small one, separated by a distance r. It's a fairly straightforward relation. The force falls off as r squared. There's a similar sort of thing for static electricity, with which you're also familiar. Notice the difference, though, that in this case, the force is developed by masses. That's what shows up in the formula. In the case of static electricity, it's charges that show up in the force formula. Otherwise, it's very similar. There's similar kinds of laws. In both cases, the force is directed along the line between the objects. It's a pulling, or in the case of electric charges, that could also be a pushing force. Notice that for masses, there's only one sign of mass charge. You can have plus and minus electric charges, which can either make repulsive or attractive forces. Gravity is different. It's not the same thing. But those are all static forces. And I'm going to be talking about something that's dynamic, a gravitational wave that propagates in time. So let's continue this analogy with electricity. Electromagnetic waves, as Fred was saying, light, radio, light, X-rays, they're all familiar to us. And we know that there's a direction of propagation for those waves, for instance, from the radio antenna all out and maybe in a sphere. But the thing that's interesting is the force that's exerted by that wave is perpendicular to the direction of propagation. And here's a little sketch to give you a feeling for how that comes about. Imagine you have an electron or some other charge, and it gets a little kick, a little acceleration, and then drifts upward. When the electron was just sitting here calmly, it had a line of force, like the static electric force that goes between the balloon and the wall, which runs out perpendicularly from the source. When you give it a kick, well, that actually makes a kink in the electric field. It has to connect to the new line here at a later time. This kick, notice, is now perpendicular, has some perpendicular component to the longitudinal one. That's what gives you the perpendicular electric field in a propagating beam. The propagation is in one direction, but the force is perpendicular. For gravity, there's a similar sort of wave. It's something that's predicted by Albert Einstein, and based on his theory of general relativity. I must admit there are other theories that have generated gravity waves, but we believe that this is the correct theory of nature, and so we work with it as our paradigm, as our basis. They're like radio waves in that they're perpendicular forces to the direction of the propagation. They travel at the speed of light. The difference is that they're extraordinarily weak, and they haven't yet been directly detected. That's our challenge. As I mentioned on the previous page, the lack of two gravity charges makes a basic difference. It's one of the things that makes for very small signals. The signal is proportional to the mass of the object, just like the radio wave is proportional to the charge of an object. Proportional to the acceleration of the masses, just like radio is proportional to the acceleration of this electric charge up here. But the thing is that because there aren't two charges, you have to make a more complicated mass combination, and you have to move it in a more complicated way to get reasonable signals. So, how can we detect these gravitational waves? Passing once again to radio waves, because of their familiarity, the way you do it in that case is You put up an antenna, which is basically a line of charges, and the radio wave falls on the antenna. It's propagating in this direction, and this is a description in space of the electric field. Or if you were to just stand in one spot here, it would be descriptive of the change in time of the electric field. It's a sinusoidal varying pattern. And what that does is to tend to, at one moment, push all the plus charges up to one end of the antenna and the minus charges to the bottom. At the next moment, to reverse that pattern. And in the third one, to go back to the original state again. So what you end up doing is sloshing the charges back and forth in this radio antenna. And that leads to an electric current, which is then detected. This is supposed to be a car, but I haven't really mastered my drawing program yet, so it looks more like a tank or something. In the case of gravity waves, we do a similar sort of thing. We imagine that there's a gravity wave now passing perpendicular to the plane of my view graph here, and it's falling on a ring of free masses. And my favorite description of this is a ring of pearls floating on a quiet pond. I'm not actually sure that pearls float. They might sink. I wouldn't try it with a pearl necklace, I think. But as this gravity wave passes, at first there's no distortion of this ring of masses. But then as the gravity wave passes, it actually distorts the ring, it stretches it out in one direction, returns to its original form, and then it pulls it in the other direction. It makes a strain in space. And in fact, the amplitude of this strain in space is something that has a fairly simple relationship to the strength of the gravity wave signal. H is the strength of the signal. And if L is the diameter of my pearl necklace, then the change in the diameter of the pearl necklace, this delta L, is just given by that simple expression. The nice thing to notice is if I had twice as strong a gravity wave, I would have twice as much distortion. If I had twice as large a pearl necklace, I would also get a larger distortion. And that, in fact, is the way that we're going to get our hands on the gravity waves. We're going to look at the distortion of space by the way it influences masses. Here's another little sketch that gives you an idea of how the light propagates along the z-axis, and perpendicular to that axis there's this distortion. So in place of using charges on a radio antenna, we'll place masses, and we'll see how they're influenced by the passing gravity wave. So what kinds of sizes of signals can we expect? Unfortunately, they're very, very small, as I say, due to this single mass charge. And one sort of experiment you might imagine making is to create a gravity wave in a laboratory. It turns out an almost ideal arrangement of mass to generate gravity waves is a bar, and you'd spin it around an axis so that it's spinning like this laser pointer is spinning. If you spun it so fast that the centrifugal forces were about to pull that bar apart, and then placed this ring of free masses as close as you could to this bar without getting whacked by the bar, you still would not have a measurable signal. It would be still too small by 10 orders of magnitude or 20 orders of magnitude, factors of ratios of the diameter of the sun to an atom that far away from being detectable. So the only thing you can do is to rely on astrophysics, as it turns out. You have to do something as violent as make a star explode or make two stars collide into each other to get a big enough signal to make something measurable. And here's a formula that gives you a notion of just how bad the news is. This is Einstein's famous formula, mc squared. It's the total amount of energy in a given mass. And imagine that 1 or 10% of the total energy of a mass was in kinetic form. That is to say, it was spinning violently, and a lot of the energy was in that motion. And imagine that this star, we're sitting at the Virgo cluster, which is the nearest collection of a significant number of stars, so you'd have a reasonable number of stars that might be ready to explode. That would lead to a strain in space of only about 10 to the minus 20 or so. And don't forget what that means. That means my circle of pearls, 1 meter in diameter, would only change by about 10 to the minus 20 meters. There's a little beast here that's come to explore the view graph. But if we can measure it, then we can learn something very interesting about the stars, and that's really what's going to drive us. It's funny, we have to go to astrophysics to get a signal, but in some ways that's a very nice thing. It gives us a good basic physics reason to go forward with our measurement challenge. So what is a good standard astrophysical source for us? There's something called a coalescing compact binary, which is basically just two stars or other objects, black holes, neutron stars, orbiting around each other, bound by ordinary gravity. There are a couple people, Taylor and Holtz, who observed such a star pair, which is in fact orbiting about once per every 8 hours. And they've looked at the rate at which that period changes. In fact, it's speeding up slightly with time, very, very, very slightly, some parts in 10 to the 6 or so. But they do see a change in that rotational rate, and it's speeding up. What that means is that the system is losing energy as time goes along. I looked at all of the possibilities for where that energy could be going, and there was only one that was left, and it turned out that if you use Einstein's formula for calculating just how much gravity wave energy would be radiated from the system, that accounts exactly for this loss of energy. And so it's almost surely due to gravitational radiation. This is a beautiful experiment. These people won the Nobel Prize for it, and boy, did they deserve it. Very, very pretty demonstration, however indirect, of gravitational radiation. Now, much later in the life of this pair of stars, in something like 10 to the 8th years, these stars will have lost so much energy to gravitational radiation that they'll be spinning more and more rapidly around each other. And in fact, in the last minute of the life of this pair of stars, they'll be orbiting once every 10th of a second, and then once every 100th of a second, faster and faster. And it's just an incredible thing to imagine masses of the order of the sun moving with that sort of rate. But that's just the kind of thing that can deliver a gravity wave that we might be able to measure. Now you see the problem why a steel bar wouldn't do it for us. We don't actually know what the end of this story looks like. It's very complicated. The two objects melt into each other. But we can make estimates for the size of the signal, at least during the earlier period, and these same numbers come up. That we would expect our ring of pearls to only be distorted by something on the order of 10 to the minus 20 meters. That's a point, and then 20 zeros or 19 zeros, and a 1. It's just an awful thing. Now, why do we want to do this, apart from the instrument challenge? I'm an instrument builder, so I think it's fun to build the instrument, but there's also really good physics behind this, and it's important not to lose sight of it. I don't think I'm going to walk all the way through this slide, but we spend a lot of time using optical telescopes and radio telescopes to look at electromagnetic radiation, to look at light and radio waves. And we learn a lot of things about space from it. But there are a number of things we don't learn, and I think the most important point on this slide is here, that radio waves and optical waves are absorbed or scattered or dispersed by all the other things that are in the universe. At the center of the galaxy, there's probably a very large black hole that's eating up the neighboring objects, stars and so forth, but you can't see it because there's so many stars around it, it's blocked from radio view. Or there's lots of other sorts of objects out in space, but they're behind dark clouds, which are not luminous, which are not glowing, but which can block the light. It's very hard to block gravity waves, and it has to do with this fact that they're hard to detect. They pass right through matter, and they don't leave very much of their energy behind. That's a disadvantage for our measurement technology, but it's a wonderful thing for astrophysics, because it means that you can look inside very deep into the hearts of a galaxy, for instance. And so this is a very strong astrophysics reason to want to pursue this alternative way of looking out at the astrophysical world. Here's a fun calculation that some people have done as to what this pair of stars looks like as it nears the end of its life. This is actually not a completely relativistically correct calculation, but it gives you a sense of it. There are these two objects, which are each one is the size of the sun, or maybe 10 times the size of the sun. They're orbiting around each other, whipping around at audio frequencies. If you could listen to this thing, it would actually sound, it would fit to your ears. And then finally, they become a single object in one great meltdown. Now, what does a signal look like as a function of time that would come from that sort of event? On this top curve, I have a plot of this gravitational wave strain, the h that I've mentioned, the amplitude of the gravitational wave, versus time. And this time here is on the order of a minute or so from one end to the other. And what we see is that while the two stars are fairly distinct entities and they're orbiting around each other like two separate objects, we get something which we call a nice clean sinusoidal signal. And it's something that we can easily recognize in our detector. Toward the end of the life of the binary system, they speed up, and then at the very end there's something that we won't be able to calculate. That we may be able to by the year 2010 or so, but at the moment it looks like it'll be easier to measure them directly than to calculate it. The waveform can change a little bit depending on whether you're looking at the edge of the star system or right on at the star system. But basically, it has that kind of pattern. The thing I wanted to now walk you through is, so this is a plot of the intensity of the gravity wave versus time, amplitude of the gravity wave. Here is a different kind of plot versus frequency and the strength of the gravity wave. And these are logarithmic measures to compress the scales, but the notion is the same, that well, as the system runs through the end of its life, in fact, it runs up in frequency, and the amplitude falls very slightly because it spends less and less time at these higher frequencies. And so this is the sort of path that our signal takes through this plot of frequency versus strain, versus amplitude. Also on this plot is the sensitivity of our initial instruments and then more advanced instruments. The thing I want you to get from this, we'll talk a little bit about how the form of this curve comes about, but we will be able to detect some of the near events with our initial interferometers so as to prove that gravitational waves exist and that they are detectable in the way we intend to do it. It will take another 10 or 15 years of development until we have sufficiently sensitive interferometers to really do the astronomy that we'd like to do. There are some other sources besides this star pair that we're fairly sure that we'll be able to see sooner or later. One is a stellar core collapse or a supernova, explosion of a star. Do notice, though, a completely symmetric explosion of a star, while it makes lots of light and maybe radio waves, doesn't make any gravity waves at all. You need to have an asymmetric explosion or an asymmetric collapse before you can get any significant gravity waves. So that's one other alternative source. Another one is something which is basically radiostatic. If you have many, many, many sources of gravity waves which are all speaking at the same time, it just forms a cacophony. It forms a background of noise which sounds like the static between stations. And this, at some level, will be an important signal source. I don't know if we'll be able to build an instrument to detect it, but one of the sources might in fact be to the initial Big Bang that started the universe. So we have a collection of sources that we can imagine. We don't know exactly how strong the signals will be. We don't know exactly how many we'll see. The thing that I'm absolutely positive of is that we'll see lots and lots of things that we haven't imagined. Nature has a much richer imagination than we do, and we've seen this again and again when people open up a new way of looking at the physical universe. There are new signals, new sorts of physical phenomena that come to light. After the fact, we can say, of course, it has to be that way. But to imagine beforehand is not so easy. So I think it's going to be a very confusing thing to look at the output of one of these detectors, but a really wonderful thing too. How are we going to get how are we going to turn the gravity wave signal into a voltage on a screen? I think that's the real challenge here. And there's a sensor known as an interferometer that's just ideally suited to this. Here's the basic notion. We take a laser, and a laser produces a light beam which is well collimated. It stays in a nice, well-aligned pencil. And we can shine it on a beam splitter, which is nothing but a mirror that has a 50% transmission, 50% reflection. And so half the beam goes off in one direction, the other half of the beam is transmitted through. They hit mirrors at the ends of the interferometer arms, as they're called. The light returns and recombines, and some of it can fall at the output on a detector here. Now, what I mean here is to suggest that we replace a couple of the pearls on our necklace with these high-quality mirrors, so that now when a gravity wave comes along, remember it will squish this circle of pearls and pull it in this direction for one part of the gravity wave and do just the opposite for the other half. That will change these lengths in the interferometer in a way which is easily detectable. Let me try and give you a notion of what the sensitivity of a detector like this is. This laser beam is a continuous sinusoidal waveform. It's a variation in time that repeats itself of the electric field. And I can draw that as a sinusoid like this. It's a sinusoid in time. If I stick myself here and place an electron in the beam, it will wiggle back and forth through the electric field. One of these arms might have an electric field that looks like this. And in fact, if the arm lengths are the same, then the two electric fields will follow exactly the same pattern because they will have taken the same path and they'll have the same delay. If I move one of these mirrors by a fraction of a laser wavelength, where that's on the order of a micron, 10 to the minus 6 meters, a tiny fraction of a hair's diameter, then I shift the pattern due to the longer arm. And the result is that where they're the same length, the two fields add together constructively, and they make a large intensity at the output here. If I move this mirror by a quarter of a wavelength of the light, then this pattern is shifted so that they're now in opposition, and the addition of those two is always 0. There's no light at the output here. So this very sensitive detector goes from the full brightness of the initial laser to 0 brightness with a motion of just a quarter of the wavelength of the light. That's just exactly the kind of motion the gravity wave will excite. And the thing to keep in mind is that the length scale for the shift from full intensity to minimum intensity is only a quarter of a wavelength of light, some part of a micron or so. Now the question remains just how well we can measure the position using this kind of system. And here I've got a sketch. This is my Michelson interferometer with my input laser, beam splitter, 2 end mirrors, and a photodetector. It's basically a solar cell. It measures how much light's coming out of the interferometer at this point. If I make a plot now of the intensity on that photodetector versus the arm length difference, then I get this cosinusoidal pattern that has to do with the wavelength of light. And you can see that this pattern would get larger if I had a larger input laser, and so that's one way I can get a bigger signal. And now the right place, you could ask, what's the right way to use this as a position sensor? And I want to try and convince you that it should be used right here at this point of the maximum slope in the signal, the steepest slope, because what that means is that for a given change in the arm length, and that is to say for a given gravity wave signal, I get the biggest change in intensity. It would be a silly thing to use it down here where that change is small. So I want to use it here, and I can make a calculation for how big that slope is. It's just equal to the input power times a constant factor having to do with the cosinusoidal function. But that still doesn't answer my question. How well can I determine exactly where I am on that curve? And it turns out that it's a very nice and very fundamental physics question as to how well you can determine where you are. And it's actually relevant for some other questions too. You can think of light as waves or as particles. You can always switch back and forth. You use the description that's the most convenient to you. Mostly I've been talking about waves until now, but I want to use now their description as particles. And the thing to note is that the light particles that come out of the laser, the photons, are not uniformly spaced in time. They come out randomly spaced. And it's very much like a rainfall, in fact. Now, if you ask, how hard is it raining? It turns out to be the same kind of question as to how well you can determine the position in this interferometer fringe. If you're at the beginning of a summer storm, and you get these occasionally great big drops on the sidewalk, and if someone were to ask you how hard it's raining, well, you'd probably measure the number of drops per minute that you heard. And if you looked at successive minutes, well, the first minute you might have 11, and then 9, 7, 14, 13. You get some range of drops. From that, you could calculate an average rainfall. You'd sum all of these numbers up, and you divide by the number of samples, and you'd get that the average value was 10 drops per minute. You're happy with that. But now the question is, how sure are you that it's 10 drops and not 11 drops or 12 drops? It turns out that for a random process like a laser beam or like rainfall or radioactivity, that the answer is that the uncertainty is equal to the square root of the average. So if you take 10, take the square root, it's, I don't know, 3.3 or thereabouts, or about 3, that you can say that you're about 30% sure that the average is 10. And that looks about right here. You can see there are variations of 2 or 3 digits in most of those numbers. Now here's the magic. If someone asks you how hard it's raining in the middle of the storm, you can give a much more precise answer. The drops per minute for this in the middle of the storm will be much higher, of course, again with variations here and there. The average of these numbers is 1,000. It's raining 100 times harder than it was before. The uncertainty is the square root of 1,000 or 30. But the thing is now, the fractional uncertainty is 30 over 1,000. You're now sure within 3% that this 1,000 is the right number. It's either 1,000 or it's 1,030 or so, but you have a very good handle now on just how precisely it's falling. So that the precision of the position measurement in an interferometer is the same kind of thing. If I look at the light that's coming out, count the number of photons, with lots and lots of light, I'll be able to tell with a good precision. And I can calculate what the precision will be from this simple square root law. It's true for all Poisson distributed random processes. So if I put that into the mathematics and ask myself how well I can do, I find the following. that if I make an interferometer with 4-kilometer long arms, and I make it long to make the signal bigger, remember that the signal gets bigger as the diameter gets bigger and bigger, and I use a laser of about 10 watts, and I use a whole bunch of other tricks that I'm not going to have the time to tell you about, that we can detect the motion of the mirrors that's due to gravitational waves. That motion is only going to be about 10 to the minus 20 of a meter. 19 zeros and a 1. That's called shot noise, by the way. There are other sorts of limits to the sensitivity, and anything, in fact, that moves the mirrors that isn't a gravity wave is something that's going to interfere with our ability to know whether or not a gravity wave has passed. And one that almost anybody could come up with is clearly going to be a problem for such a detector is seismic noise. There are lots of different kinds of seismic noise sources. There's honest seismic activity, little tiny earthquakes that are taking place throughout the Earth at any given time. There are ocean waves that in fact shake the ground quite remarkably for hundreds of kilometers, or miles if you prefer, inland. Wind and rain also can shake the ground. People are a big source of noise, and one of the important things in this experiment is to get as far from people as you possibly can. The bottom line is that we need to reduce the seismic noise by about a factor of 10 to the 8th. And that's another one of these phenomenal factors. To give you a sense of it, suppose the Earth were moving back and forth by a kilometer. It's sort of like a half a mile or so. We would need to reduce that motion to less than a hair's breadth of motion. So it turns out the ground starts out at less than a hair's breadth of motion, and we have to go all the way down to this 10 to the minus 20 meters or so to succeed. But the way that we do this is remarkably simple, I mean to say. We use the fact that masses like to sit still. Imagine I have a mass on a spring, and I attach this support to the ground. If I move that support very slowly, you know that the mass is simply going to move with the ground. If I move it at the resonant frequency of the mass, you probably have the experience of seeing a very large amplitude of motion on the object that's suspended on that spring at the resonance, and it depends upon the losses in the system how big that motion is. But here's the trick: if you move the ground much more quickly than that resonant frequency, the mass will tend to sit still. It'll tend not to move. And in fact, as you get to higher and higher frequencies, it moves less and less. Here's an approximate expression for it. It goes as 1 over the mass times the frequency squared. So as the frequency gets larger and larger, this factor becomes smaller and smaller. So this is an isolation system. It's a way of reducing the actual physical motion of an object. Let me give you a nifty sketch of what now our pearls look like, the mirrors that we use to sense the motion. The object itself is this blue cylinder, and that's a mirror. One surface is very highly polished and coated so that it has a high reflectivity, and it's suspended in a simple wire sling to form a pendulum, and that gives us this isolation that I mentioned before. One such sling doesn't give us all the isolation we need. I'll show you on the next page our other trick for that. But this is a nice way to start out, because in addition to isolating, it also lets us orient this mass. It lets us position it. There are very strong requirements on exactly how you hold that mass. So that's what all that other stuff is in there. But the basic notion is just a pendulum. Now you can actually take the same idea and put layer on top of layer to get more and more isolation. And that's what we do, in fact. We take a number of big masses and separate them by things that look just like chemistry rubber stoppers. And what you find is that each one, if you place this on the ground, each one of these successive layers is moving by a smaller and smaller factor until we get to this level of isolation that we actually require for the instrument to work right. So this is all words, and it doesn't give you at all a sense of what we actually do in the laboratory. This is the sort of designing that we have to do. The sort of experiments we do in the laboratory are really fun, in fact. We take these ideas and we test them to make sure that they're right. We test to make sure that we don't have any technical problems that interfere with the basic noise sources that we have, like shot noise. And here's such an experiment, in fact, that's designed just to look at this shot noise, the fact that we have to look at sort of 10 to the minus 10 of one of these full optical fringes to make our measurement. And it consists of, well, here's that Michelson interferometer that you saw before. It sits inside a vacuum system. I'm sure you've had the experience of driving along in the summer and looking along a tarmac road and seeing the shimmering of the light, it's due to the turbulence of the hot air that's rising from the tarmac. That would be a noise source for us. It would look to us like gravity waves are passing all the time, when in fact it was just a hot day. So we have to place the entire system in a vacuum chamber. We have a high-power laser that's got various kinds of stabilizations attached to it so it won't add any additional noise. What does this thing look like? In fact, I've got a couple of photographs to show you just what an experiment in our laboratory looks like. And I also want to add that the size scale, I mean, this is an experiment that 2 or 3 scientists and 2 or 3 students will spend 2 or 3 years on. And students will get their PhD theses from it. Here's a photograph of the vacuum system that I just sketched. It's sort of person-sized. If you open up one of the tanks, here's a photograph of that. Maybe a little bit hard to understand. I'll try and explain what we're looking at here. These are these seismic isolation stacks that I mentioned before, these layers of metal and rubber. And then there are wires that climb up the side that are attached to each successive level to make sure that their motion won't shake the top table. The entire system is sitting inside a clean chamber so that there will be no dirt that gets in on the mirrors. And then there are the Michelson mirrors. There are actually 1, 2, 3 mirrors inside here that are suspended as pendulums, as I described before. And here's, in fact, one of our postdocs, Gabriela Gonzalez, who's in the process of adjusting one of these mirrors on a suspension. Perhaps I'll shift it just a little bit. There's a wire which it's hard to see, but there's a very fine wire which starts here and loops around this bluish object, which is our test mass, and comes back up again. And then here are the control systems that allow us to orient the mass and so forth. So it's a human scale experiment. You get your hands around it. That's nice. Here's a close-up of one of our mirrors. And oh yeah, you might just about be able to make out this wire which is looping around, coming around, and coming back up again. This is a very high reflectivity mirror. It looks funny to the eye, but to the laser beam, it looks like a very, very good reflector. And I think at this point, the thing for me to do is this is largely what Fred told you when he started out the talk. I've had sort of a funny career, and I think it's important to say something about how I got to the point of being involved in this experiment. And I want to put it at this juncture because it's really building the kind of experiment for which the photographs I just showed you, that's what excites me here. I've lived on the 2 coasts, and I think that the initial influence in my life was my father. He's a psychologist, and it was in the good old days when doing psychology experiments meant running rats around mazes and building trap doors with little switches and counters to see how many times the rat ran around and so forth. I thought that was just wonderful. I thought that was what life should be, is building little mazes like that. Went to high school in New Jersey, which is an awful thing. Spent some time at undergrad at Tufts. I actually never finished at Tufts because they had a language requirement. You had to be able to speak German to get an undergraduate degree, and I didn't want to make funny noises in front of people. I then went to MIT as a lab technician, where I met Ray Weiss, Professor Rainer Weiss at MIT. And I think this is the second key thing. I found a mentor. I didn't realize at the time, but I saw this person. I saw the work that he did. I saw his approach to doing science and actually to doing life, and I said, I like this. I want to follow in his footsteps. And I don't think I've been steered wrong. He taught me a great deal of physics, but he just taught me a dedication to the idea of doing good science. I think that's something, if you find a mentor, you're likely to latch into science. Worked first on this cosmic background explorer, but then I started to get excited about interferometric gravitational wave detection because it was actually something that Ray invented himself back in 1972. And what I discovered is that I wrote a letter to a German group that was doing this kind of work saying, would you like to have a visitor for 6 months? And they said, sure. And that bootstrapped me into this business of a fair amount of travel, learning a great deal both in Munich and in Paris about physics, but also about different cultures. I hadn't realized that science would be such a wonderful way to tour the world. I get to go to conferences all over the world every year, not very many, but one maybe. That's enough. It's a very exciting part of my work, and it's something that I treasure. So I'm back at LIGO now, and it's sort of big science. I think I do more managing than science now, which is sort of a shame, but it's still lots of fun. I'm looking forward to getting back into the laboratory again. So let me tell you, sum up what the initial interferometer looks like, the initial LIGO interferometer. There are lots of things in the list I didn't talk about in any detail, and I'll sort of skip over them. But on the side of optics, we use this Michelson interferometer as the way of reading out the strain, the actual measurement device. Need to have a fairly powerful laser so that the shot noise source won't be too big. We have to have a vacuum system to control the noise from other sources, like the residual gas. And then we have some baffles and folded optical paths I didn't talk about. The interferometer is a bit more complicated. On the mechanical side, let's skip over some things we're not going to talk about here, but one important thing is that we have these very long arms. That makes our gravity wave signal bigger. The seismic noise doesn't get bigger as the arms get longer, so we get to get an improvement in our signal to noise ratio by making the system longer. And here's, between this vacuum path and the 4 kilometer long arms, you get a picture of the size and the magnitude of the undertaking. Then we attenuate the seismic noise. One thing you might say is, well, why not do this in space? There's no seismic noise there. You have a good vacuum for free. Well, it's not a bad idea. It's certainly something that will happen at some point in the future. It turns out you pick up other kinds of problems. Instead of having seismic isolation, excitation from the ground, you have solar wind which buffets the test masses. And what you have to do is to build shells around your test masses, make them follow your masses around. It's not such an easy thing to do. It'll get done, and it'll be a good experiment, but it's for your generation, maybe not for mine. Well, with that, I think what I'd like to do is now switch over to talking, instead of about basics, about LIGO itself. As I say, it's a couple of sites separated by 3,000 kilometers. Here, a map of the states. It shows you where the two are. One is on a Department of Energy reservation here in Hanford, Washington. It's extremely flat, extremely quiet, desert-like. And then the other one is in Louisiana. It's actually in a forest. It's a little bit swampy, but there aren't many people there. There might be a lot of poisonous snakes, I'm not sure. Each one of these two sites is capable of multiple interferometers because we have a great big vacuum system. We'll be able to put a number of different laser beams through it for different kinds of gravity wave searches. One of the important things to note here is that we will be looking for signals that are simultaneous or near simultaneous in these two detectors. And why is that? Someone up here in Washington may drop a hammer on the outside of our vacuum system, and we say, there's a gravity wave. It's very unlikely that someone will drop a hammer on this apparatus at the same time, and by comparing the outputs of the two signals, we'll be able to eliminate that as a possibility, as a suspect gravity wave. The other thing that's neat about it is that you can do some triangulation. Suppose you see a signal which happens at exactly the same time in both of these antennas, then you know it comes from a gravity wave which is situated in angle directly between the two sites. If it's angularly closer to one of these others, to one or the other site, then the signal would arrive first. And in that way, you can actually determine about where the signal is coming from. Now, this LIGO interferometer system is going to stay in place for about 20 years. And we wanted to make our envelope flexible and big enough so that we'll be able to accommodate all the changes in technology to be able to work toward this true astronomy of gravity waves that I mentioned before. So it'll be around for a while. You'll have a good chance to use it at some point in the future if you're interested. Let's look at some photos. I think that's more fun. Now that we've gotten through the hard stuff, let's show you where this project actually is in terms of being built. Now this photo is half a fake. It's a real photograph, aerial photograph of the site in Louisiana. The site in Washington isn't much fun to look at a photograph of because it's desert. You can't see where you've cleared the way. So there are these two 4-kilometer long arms, and the part that's a fake is that someone's taken a computer system and drawn in fake buildings which don't quite exist yet in the place. But it gives you a sense of scale. It goes over roads and farms and so forth and so on. Let's zoom down now and take a look at what one of those arms looks like in construction. I think this is neat. Now, these arms have to be straight. We have to shoot laser beams down it, and if the tube is not accurately aligned, the laser beam would hit the side of the tube. So in fact, over this 4 kilometers, some 2.5 miles in length tube, there's only 3 millimeters, or I don't know, it's an eighth of an inch or so, of misadjustment of the tube. It's a remarkable thing. It's due to the GPS technology, global positioning satellite technology. It's really good stuff. So this bed that you see that's laid down here is flat. And it's flatter than the Earth, in fact. The Earth is curved, and over a 4-kilometer distance, that curvature is non-negligible. Our line is actually flat and had to dig out a little bit of Earth in the middle to accommodate the fact that there's this curvature to the Earth. What you're looking at here, though, is the steel which goes on top of this bed to make sure that the system will remain stable and stiff. And here's, I think this is a great picture. There are these people who make their living by making highways. And they've built these wonderful machines. You put them down and you turn them on and you make them roll. And in the front of it, there's nothing but a bed with a bit of steel, and behind it, there's an interstate highway. So we've built the LIGO interstate highway. It's 4 kilometers in this direction, 4 kilometers in this direction. It doesn't go anywhere, brilliant. But it's a wonderful thing to see this band of concrete coming out of the backside of this truck. So that gives us nice, flat concrete beds on which to put these vacuum tubes. What do these vacuum tubes look like? They're about 1.2 meters in diameter, 4 feet or so. And here some people are actually building the tubes. They're rolled out of spiraled steel. And people then put some reinforcing rings on them to hold them in place. When they start out, they're actually kind of dirty inside, with oil from manufacturing and so forth. So they get baked in these containers, pumped out to make sure there are no leaks. The remarkable thing is they've made hundreds of those now without a single leak. Here's some poor fellow he's inside one of the tubes, and he's installing a baffle. It's a light trap. It keeps scattered light from interfering. There are people who are actually going to go inside these tubes and travel kilometers, the better part of a mile, to put in baffles. It's not a job that I'd like to have. Now, putting down this tube on this flat roadway is a pretty straightforward thing to do, and you might ask, why not just leave it like that? It turns out there's a funny thing about the United States. Everybody has guns. And anytime you've got something that's out on the horizon and there aren't too many people around, people are going to take pot shots at it. So we have to build a cover that goes over it to protect it. The thing that's sort of scary, continuing with this notion of what people do when they've got guns in the countryside, is that it turns out that if you ask the advice of experts, they tell you you need 6 inches of steel reinforced concrete to keep hunter's bullets from puncturing the cover. These are people looking for what kind of animal, I'm not sure what. So at any rate, here we have our vacuum tube, which is covered by this nice rigid structure. It serves other purposes too, but it's crucial to protect the tube from pot shots. Going down in the desert up in Washington State. Now let's look at the point where those two lines come together. This is where the beam splitter of our interferometer will go. This is the center section of the interferometer. And even as we speak, well, maybe not at this moment, but a little bit earlier today, people were in the process of building this building, which is going to go in at that juncture of the 2 arms. You can see the two of them coming together. And we'll be looking at what goes on inside this building here. This is actually the current state. Let's see, what was it, as of a month or so ago, of the steel that's going up to build that building. So let's imagine that a tornado comes along and strips the roof off of that building. What do we find? We find this collection of the vacuum system. Let me identify for you where this poor Michelson interferometer has disappeared. There's a laser here. It comes into the beam splitter and is split into the 2 arms and shoots down 4 kilometers in each direction. This second collection of chambers is for a second interferometer, which lies by the side of the first one. So what do these chambers look like, in fact, in reality? Here's one that's being fabricated. It gives you a sense of scale. It's big, and it's big to accommodate that seismic isolation system I described to you. It's bigger than we really need, but again, we want to make sure that we've got a system that can grow with us into the future. Once this whole system's together, then we'll have this nice, flexible laboratory space with these modular vacuum components that will be able to mix and match as people come up with new ideas. When you folks are in graduate school or beginning professors, you'll come and tell us where we have to move these things to do your experiment. And the neat thing for me is that this is all going together right now, and will not be very long until we can actually start installing and testing our optical components. I'm going to stop there. I've got the usual nice last slide that's supposed to give you a warm, fuzzy feeling. What's our goal here? It's a gravitational wave astronomy. It's a window on extremely dramatic events in space. The first step is to make a direct detection of gravitational radiation. This will prove Einstein's theory is correct and prove that we're on the right track for building a system that can make gravitational wave detectors. And we think we'll be able in a position to start observing in the year 2001, which sometimes looks very, very near to me and sometimes looks very far away. Along the way, and this is really really the reason that I'm doing this experiment. There's some very nice fundamental physics, things like the shot noise. It's very simple, and yet it's very fundamental, but also very pretty technology. The toys are just fantastic. I think that that'll stop. Thank you.
Thank you, David. Very interesting talk. Would you entertain a few questions?
I'd be happy to.
I'll let you lead.
Please.
On your goal then, on the goal, it said that it's a window of extremely realistic events. Well, I don't understand what that meant. I didn't really understand what the whole point of studying gravitation.
There are a lot of things that happen in the universe that we are sure are happening. A lot of things they must be happening because we know that the elements are there for them to take place, but we haven't been able to observe them. And such things are black holes gobbling up nearby stars. We don't have any direct signals from that. We call that a relativistic event when the velocities are large compared with the speed of light. It means that the kinds of physics that goes on is very strange to us, stuff with which we're not at all familiar. We're not at all sure that our understanding of nature is correct to describe those sorts of events. The gravity wave signal that would come from a star falling into a black hole is something that we could use to infer what's going on in that black hole, and will teach us about the physics that's there. That's our motivation. It's a new signal to get some information about what's happening.
So the gravity signal goes through Earth, from outer space, it just comes through Earth, and that's why you have two different points.
Yeah, it passes through everything, including the Earth, and leaves a little bit of energy behind in our mirrors by moving them a tiny fraction. By looking at those two signals, we can say something about what happened in that terrible event.
All right, thanks.
Sure. Other questions? Please, in the back. How much does this cost? It costs about $300 million. It's sort of interesting to put that in perspective. There was a project to build a superconducting super collider, which is no longer with us now. This cost is much less than the uncertainty in the cost of that project. It's a tiny fraction of one good-sized airplane. It's
only $1.50 for each person in the United States. That's a bargain, right?
Well, it's still a fair amount of money. People do ask and should ask the question, wouldn't it be better to give $1 million to 300 good researchers? Wouldn't you get a lot of very good science out of that? You surely would, but you get a different kind of science out of this. What I hope is that our society can support both those 300 researchers plus a couple of experiments of this scale. It's expensive. Please.
If the truth would be wrong, you can't find gravitational waves, so we like gravity.
It would be the question was, suppose we don't see anything. What's the consequence of that? It would actually be very exciting. General relativity looks like a really good theory now. There are a lot of, like that first measurement I said, the people who have just observed this change in rate of a pair of stars, that works out just perfectly with the calculations of general relativity, and no one has seen any faults in general relativity yet. If with our measurement we got to a point of sensitivity where we knew that we should be seeing signals but saw none, it would mean that we'd have to re-examine one of the most important bases of physics today. And so it would be a really striking conclusion if we said general relativity is wrong. People wouldn't believe us. They'd say our instrument wasn't working right. That's what it comes down to. Please.
Does the gravitational wave dissipate as it goes along?
Does the gravitational wave dissipate as it goes along? Very, very little. It's again the story. It has a very weak interaction with anything, and that means that you can. Once it starts, it propagates until it reaches the end of space-time. And it leaves very, very little signal behind it, which makes for the challenge in instrumentation. But no, it loses very little energy as it propagates.
Could I ask one, David?
Please.
You go to great lengths to make your detectors insensitive to seismic noise. Have you excited geophysicists about actually turning the thing into the world's most sensitive seismograph?
We've talked to them about it. But it's a funny thing. We do everything we can to be insensitive to what's most interesting to them. They like to look at fairly long time changes in the distance between 2 points. And there are, in fact, a number of laser interferometers that have been laid down specifically for that purpose to measure this distance change over time. And it moves by creaks and cracks, but it flows in one direction or another according to whether or not you're on the same plate and so forth. We do everything we can to forget our relationship to the Earth. And while you could insert a bunch of technology into our beam tubes and at our vacuum stations to measure those changes, it is actually not a very interesting place to do it, because the other point is we choose sites that are very, very uninteresting seismologically. We want the quietest places in the world. So it didn't work very well with that sales job. We actually Ray tried one other thing. He tried to sell it to the military. He said, if a satellite passes overhead, we'll be able to see the change in gravity due to the fact that there's a massive object here, and that will move our mirrors ever so slightly. And Ray tells me that the generals looked at it and they smiled and they said, thank you very much. We have other ways of doing that. So didn't fly.
Well, let's thank our speaker. I'm sure he'll stay around for a few extra questions.